All right. Hello, folks. Today is all about polymorphism, or at least mostly about polymorphism. I have a few notes to talk about that sort of finish off a few things that we did last time, some notes on overriding and stuff. But for the most part, today is talking about polymorphism, and it's really a concept that you have to really see to understand. I could give you sort of a one sentence version of it, but it doesn't make a ton of sense until we actually see it in action. So that's going to be a lot of what we do today. And then, of course, the blackjack game that we work on, we will see it a little bit there as well, sort of in a similar way that we see it today, but obviously in a bigger project. So I have a couple notes related to overriding. So an instance method. So let's say we had a method that existed in some superclass. It can be overridden only if it is accessible. So if you have a private method in some superclass, you cannot override it because it's not accessible to anyone outside of its own class. If you define a method in a subclass that uses the same name but is private in the superclass. So in other words, you have the same name in both classes, the same named method, but it's private in the superclass. The two methods are then completely unrelated. They're not actually an override of each other. And remember, in Eclipse, we saw that it sort of notes in the side, the typical sort of thing is called the gutter, the sort of very side next to the line numbers. We saw a little arrow, and that arrow was saying that this is overridden. Well, in this particular case, if you had a subclass and a superclass, they both had the same method, but the method was private in the superclass, then you would not see that. It's not actually doing an override because the method is not accessible in the superclass. A subclass can, of course, override a protected method in the superclass. The whole point of the keyword protected is that your children, the child classes, can see it and use it, but no one else can. The subclass can also change its visibility to public. It can make it less restrictive. But a subclass can't reduce the accessibility. So it couldn't take it from protected to private, or even from public to protected. So you can make it more accessible, but not less accessible when you override it. Now, these are things that you're probably not going to come up against sort of very, very often. You're not going to see something like this and go, oh, I can make this public, but I can't make it private. You're not going to sort of see that sort of thing that often, but it does come up. And so occasionally you might think, okay, I'm going to make this private and then that'll work, but then you might get an error. And likely, if you're messing around with visibility of a method in a subclass, it might be related to some of these notes. So real quick, we talked about visibility last week. I just want to give you a quick sort of overview again, because we've talked more about specifically what this protected modifier means. So your data fields and your methods have these visibility modifiers that define what other classes can access data or invoke the methods. So your four visibilities are public, private, protected, and package private. Package private is when there is no modifier. So a public data field or a public method can be accessed within the same class, within the same package, within a subclass, or within the entire world. In other words, anybody can access it. When you make a call to scanner.nextInt, that is a public method within the scanner class, because you are not in the scanner class when you write that call. You're not in the same package because that comes from Java util. You're not a subclass of scanner. You are in the world. You are just existing in the world of Java. And so as long as you have access to that class, you can call the method. So as long as we access it using our Java util scanner. Now, protected is similar, but it has to do with subclass. So within the same class, of course, you can access a protected variable. Within the same package, you can, as long as it's a subclass. So as long as you're a subclass of some other class, you can access protected variables. If you have no modifier at all in front of your variable or your method, then within the same class and within the same package can access it. And if you put private, that's the most restrictive. You can only access a private variable or a private method within the same class. And we've seen that with data. Not as much with methods, but with data, that's what we've seen. We've seen that we cannot access, say, our circle.radius outside of the circle class, which is why we would then write a getRadius method, for example. So these are the typical visibilities that you're going to come across, and they're fairly ubiquitous. You're going to see sort of this style of visibility in a lot of different languages. The no modifier might be replaced with something else if you've used C# in the past. The no modifier here in Java would essentially be replaced by internal. It's just a different word for essentially the same thing. So you will see public, protected, private in almost every language, with maybe one or more additional modifiers that you'd have to look into. Like instance methods, static methods can be inherited. Remember what static means. Static means there's only one that exists for any of the object. It's sort of a per class thing, not a per object thing. But static methods can't be overridden, so they can be inherited. So a subclass can use it, but they can't be overridden. So if it's defined, if you have a static method and it's defined in a superclass, and then you redefine it, you write it again in a subclass, then you hide the one in the superclass. There's this sort of hiding going on. And we talked about this sort of hiding when we did scope in our review, and we talked about scope. It's the same sort of process here. If you write a static method in both a superclass and its subclass, then the superclass one is hidden when you make an object of the subclass. So it's kind of like overriding, but it is subtly different, because the sub and the superclass can sort of access both of them. So it's subtly different from a sort of a practical standpoint. If you needed to do this, you probably wouldn't notice the difference, but it is subtly different. So I just want to show you a quick example here. This has this sort of has all the static methods. Are all static methods in these two classes. So we have this superclass here, and we have this subclass here, and I put main within the subclass. So our point here is to look at these 4 calls. Remember, these are static methods, so we can call them just by using the class name, dot, and then the static method name. So if we start here with super.m1, I'm going to go to the super class, which is this file over here, and I'm going to call m1. So it prints this. So m1 is here. It's static. That's why I can use the class name, and it prints super m1, which is why we get super m1 for the output. Then I call super m2, same thing. The super class has a super m2 method, which is why we get this super.m2 for the print. Now, if I call sub.m1, we look at the subclass, that's this file here, and we see that sub extends super, but there's no m1 function. All we have here is m2. Static functions, static methods are inherited. So if I don't find it here, I look up, follow my extends to super, I come over here, I say, oh, here's m1 right here, and that's what I've run. So even though it's sub.m1, it still runs the inherited version of m1. So it did get inherited. But there's some hiding going on here as well, because I have an m2 in sub, and I have an m2 in super. Now, it didn't matter when I called super.m2, because we went straight to the super class. But if I call sub.m2, it does hide super m2. It hides this one. I only can run the one in sub by calling sub m2. And so that's why we get the sub.m2 printed here. So this is the idea of things that happen when you use static methods and sort of dealing with inheritance and some of this hiding. Again, it's a subtle difference that there's this hiding happening rather than an actual override. So it's not actually being overridden, specifically M2 in this case. It is actually hiding the superclasses M2. All right, so a sort of last little thing on some of this visibility stuff. I just want you to think about a question here real quick. What are the effects of keeping all of a class's constructors private? If I made a private constructor and that was the only constructor, or if I made all of the class's constructors private, if I had more than one, what's the consequence of that? I think one of the obvious ones is that you can't instantiate the class outside of the actual class itself, outside of the sort of the class's file, right? Because I wouldn't be able to call, let's say it was our dog class we were working on. If I made the dog constructor private, then I wouldn't be able to say dog D equals new dog, because that constructor, that new dog that I'm trying to call, it would be private, and I can't access private things outside of the same class. So I wouldn't be able to instantiate it outside of the class itself. I think that's one of the more obvious ones. But there's one related to OOP as well, or at least the stuff we've been talking about, the more recent OOP stuff we've been talking about. The class wouldn't be able to be inherited either. You wouldn't be able to make it a superclass of some subclass you had. The reason for that is because, remember, we have to call super when we write our constructors for the subclasses. And if super is not accessible, in other words, a private constructor, then we would not be able to access that, and thus not be able to write a subclass from that type. So the two sort of situations that sort of should come to mind when you're thinking about a private constructor is that no one outside of the class can instantiate the class, and the class cannot be inherited. So some of these visibility things do have important consequences. A bit later on in the semester, I will show you an example of a very, very useful class, or at least a useful sort of piece of a class that relies on a private constructor. I've gotten this question before when sort of going over some of these slides, is why would you ever even use a private constructor then? You can't really, it seems like you can't do anything with it. But there's some really cool things that you can actually do. So that's something that we'll look at a little bit later in the semester. There's another keyword that you may have noticed in the homeworks. Pretty much at least all of the variables that I give you, so those strings that sort of show you what the errors should look like, they have this final keyword. And I know we talk a little bit about this in CS1, or at least I end up talking a little bit about it. It has a few uses. Typically, you're going to use it for something that is a constant, if you're using final with a variable. So the first example here, final static double pi, and you put in pi to however many digits you can remember. Typically, when you do this, you make the variable in all caps. So you know that it can't be changed. It's a constant. It's all caps. If you use the math library and you use math.pi, the pi there is a constant. But you can use final with classes and with methods as well. It's not just restricted to variables. So a final class cannot be subclassed. So you see here, final public class, end of the line. So it literally is the end of the line. If you think of like a giant inheritance chain, I drew some of those pictures in the last lecture, just boxes with arrows. A final class, you cannot make a subclass from that. You cannot put another class below it in your inheritance chain. And a final method is sort of similar, but it can't be overridden. You can't override it in a subclass. So it's essentially the last word on that method. So you can use final in these different contexts. You probably won't in most of the sort of stuff that you write, because it is more of a thing that you would think about sort of after you do your implementations. You'd be like, oh, this class probably shouldn't be subclassed, so I'll put final here. It's not something you necessarily write as soon as you write the class. It's something you would probably add in later. But as you get more experience, then you might realize that, oh, I don't want this to be subclass, so I'm going to put a final in as soon as you write it. That's a perfectly sort of a possible thing to do. Okay, so I want to go back to pet. So I have the pet class. This is basically where we left off last time. And I did change my main a little bit, so I'll show you that here in just a second. But I want to show you this, at least talk a little bit about this simple one first. So in this little main example here, I've created a pet object. But now remember, we need a name and we need an ID when we create one of these pet objects. The question you would probably ask is, what is this pet? We have a class for dog. We have a class for cat. If we wanted to make any more pet types, we would probably just create them as a subclass of pet. Pet is just the generic stuff that we had in both classes. It's never really meant to be a object that we create, because what is a pet? What type of animal is a pet? Well, it could be many types of animals. So does it make sense to create an object of type pet? That's the question. That's the question I'm trying to ask about this particular class. Does it make sense? We already know that, well, the pet doesn't, we don't know what the pet says. What does a generic pet say? I don't know. So this idea of a generic class can cause a problem, because I don't want anyone, let's say I come back and I use the code later, or someone else needs to come in and mess around with my code and extend what my application does. I don't want them doing this. I don't want them saying pet p equals new pet, because it doesn't mean anything in this context. The dog and the cat do. The pet class was just a convenience, so we could reuse code. It's more of a coding type of thing, a coding result, rather than an actual sort of physical result, a physical pet. So this is where we get abstract. So there's a new keyword, abstract. And it has two contexts, for methods and for classes. And as you might guess, we will be making two things, a class and one of the methods within the class, abstract. So an abstract method, as soon as you put this abstract keyword in, it's a method that is declared without an implementation. Whenever we write a method, we would always put, public string, here's our public string says, and then we'd have our curly brackets, and we put our stuff in here, whatever we wanted this method to do. Well, for an abstract method, you do the same type of thing. You still put the signature. So the signature is all there. We put abstract in front of it, and then we just put a semicolon. That's it. So we're saying this method exists, but we're not going to fill it in. We'll leave that to a subclass. Now, if a class has even one abstract method, so if you write a whole class and you say, all right, I want an abstract method, then the class itself must also be declared abstract. So you do the same thing. You just throw abstract in front of your public class and the name of the class. You still have all of your stuff in that class. You have all your stuff in there still. But that abstract keyword in front of the class has some profound implications. An abstract class is a class that is declared as abstract. It doesn't have to have abstract methods, but if it does have abstract methods, the class must be abstract. Okay. So that's just sort of the little sort of caveats to go with it. Now, an abstract class cannot be instantiated. If you make a class that is abstract, it cannot be turned into an object. You cannot say, so if we did this to pet, you cannot say pet p equals new pet. We could not do that if pet was abstract. But abstract classes can and probably should be subclassed. The opposite of an abstract class is a concrete class. So what we're about to do, we're going to go into Eclipse, and we're going to make pet an abstract class, and we're going to make says an abstract method. So this will give us one abstract class and two concrete classes, along with one abstract method. So let's go do that right now. Over here, and we'll go to pet. All right. So the only thing I need to do to make this abstract is type in abstract. And that's it. I've created an abstract class. So I can no longer do pet p equals new pet. And I'm going to jump over to main, and we're going to actually try it. And then I want to take says. And I'm going to do the same thing. I'm going to make this abstract as well. That means we don't need the implementation. So I can get rid of the brackets, curly brackets and everything inside, and just put a semicolon. So I now have an abstract pet class with an abstract method called says. This being abstract means that any subclass, and I should use the any concrete subclass will define what this does. That's what making an abstract method means. If you create a concrete subclass, it can define what this does. I don't have to define it here because I don't want to. It doesn't make sense for me to define it here. Now, I did change main a little bit to reflect some of the stuff that I'm going to show you in a couple of slides, but we'll talk about that in just a second. But if I try to make a pet p and create a new pet and put in, a string for a name and some ID number, it won't let me do it. The error here says cannot instantiate the type pet. Notice where the error is. The error is actually not over here. It's not on the left-hand side of the equals. It's on the right-hand side of the equals. That's actually important. When we talk about polymorphism today, you're going to see why. You're going to see why the left-hand side doesn't get the error, but the right-hand side does. It's a way that we can sort of use polymorphism to our advantage. Is something that's sort of a consequence of what you see here, or sort of a side effect of what you see. All right, so we have new pet, some name, some number. Doesn't work. We cannot instantiate a new pet. We can never say new pet. We can only create dogs and cats in that way. All right, so here's those changes we made. So again, the benefits here are that we cannot directly make new pet objects, and that's good. We decided it didn't make sense to create a pet object, so this abstract immediately makes it so we can't. And then as soon as we make some other concrete, say a cat or a dog or a bird or whatever, they implement says. And we've already done that. If we go back to the code and we look in dog, we already implemented says. We already wrote says. If I didn't have this, I'll show you what happens. If I didn't put says in here, there's an error on my class dog. It says the type dog must implement the inherited abstract method pet.says. So Java knows and Eclipse knows, hey, you have an abstract method. This is a concrete class. So it must define what says is, what says does. one of the cool things about this, and something that you can sort of rely on here, is that if I hover over dog and I see that message, one of the quick fixes is add unimplemented methods, and if I click that, it fills it in for me. I have to put in what it actually does, but it writes all of the other sort of initial code, which is kind of nice. So then we can say put this woof back in here. So Eclipse knows that you need to do things like this. If you have an abstract method or something, Eclipse knows that, hey, you need to put this in here. All right, so visually it's going to look like this. Typically what you see is, and it's a little bit tough to see here on PET, but an abstract class is typically italicized, the name of the class, and any methods that are abstract are also italicized. So it's just a little bit more that you can tell from the, a little bit more that you can tell from the UML diagram. Down here with cat and dog, they don't really change at all. We still have says as being a concrete says in both of them. But what this tells us, if you sort of look closely, is that, oh, says is abstract, so every single subclass that I create must include a says method. That's probably going to do a different thing. All right, so by making that change, you don't really have to change anything that we did previously. And I went and sort of added this stuff with the arrays back in. It was on the slides from previously, but I didn't want to clutter things up too much. So I'm going to talk about this now back in Eclipse here. There's not a whole lot of sort of important stuff that's happening here. It's just creating two arrays. Put my pen here. So it's just creating two arrays, an array of dogs and an array of cats, and I create a couple of dogs and cats. So here's element 0, here's element 1 for the dogs, and then element 0 here and element 1 for the cats. So we got Spot and Rover and Mittens and Garfield for our dogs and cats. And then all this does is it goes over all the dogs, prints out what they say, goes over all the cats, prints out what they says, and if that particular cat has hairballs, which in this case Mittens has hairballs, then it says clears throat. So if I run this, it's just going to print out my two dogs from my array and what they say, and then the two cats and what they say. And again, if it has hairballs, it will do this clears throat thing. So that's all this is doing. It's almost the same as what we did last time, just with sort of more dogs and more cats. Now, I wanted to make sure that I wrote this because I want you to see how this is going to change. Because by making our pet abstract, it didn't really change anything from the slides from last time. This still all works. I didn't change anything else. I literally put the abstract here and an abstract here, deleted a little bit of code, and everything still works the way it did before I added in that abstract stuff. So it didn't really bias a lot, making the pet abstract. It made it so we couldn't say pet p equals new pet, but that's sort of been it so far. So this is where we really start to see polymorphism in action. So let's jump into that. So polymorphism, sort of a one sentence sort of description, is a variable of a supertype can refer to a subtype object. A variable of a supertype can refer to a subtype object. It may take a little bit to sort of fully understand this, and we're gonna talk about sort of several sort of different ideas related to this. We're going to go all the way back to our primitive types, doubles and ints and stuff like that, to think about what this means. So remember that a class defines a type. A dog is a type, just like a double is a number. A dog is a more complex type that might have some numbers and some strings associated with it. So a class just defines what a more complex type is. A type defined by a subclass is called a subtype, and a type defined by a superclass is called a supertype. So dog is a subtype of pet, right? A dog is a pet. And a pet is a supertype of cat. Object, I mentioned this briefly last time. Object is the supertype of all classes. So I want you to keep this in mind, this sort of subtype, supertype idea. All right. You should have seen casting before, way back in CS1. Casting is just used to convert an object of one type to another. So for primitive variables, for example, going from an int, so on the right-hand side, we have an int, to a double, the type on the left. This is implicit. Java does this for you. You don't have to do anything. If you wanted to explicitly do this, this will give you the same result, the second line, but this is sort of effectively what Java is doing for you. You don't have to do this parentheses double, but Java is doing it for you in this case. But if we go the other direction, if I have a double on the right and I want to change it to an int, or I want to save it to an int, I must do the cast. So you must explicitly cast, like that third line, when moving from general to more specific. General to more specific. A double is more general than an int because all integers are doubles. All integers are doubles. This is just 5.00 and so on. But all doubles are not integers. Clearly, this is not an integer. So general here is a double. Specific is an integer. So in the case of objects, so this is just for the couple primitives. For objects, when you go from superclass to subclass, the superclass or the supertype is more general than the subtype. Pet is more general than dog. Pet is more general than cat. So when you go from general to more specific, you must do a cast, and that's something we're going to see coming up soon. All right, so object-wise, you saw the primitive stuff. So object-wise, it sort of looked like this. If I created an object that I call O1, and I set it equal to a string, this will work because all strings are objects. Remember, object is the supertype of all classes. All strings are objects. But the next line here, where I try to say string S1 equals O1, we know O1 is a string. But Java will not let us do this because not all objects are strings. We know, just because of the way the code's written, that O1 is a string. But Java knows it's an object. O1 is an object, according to Java. It might contain a string, but there's no guarantee. This would be going from general to more specific. And we must do a cast. So the code for it to work would be this. We must do the explicit cast to string. The check here, because object might not be a string. If I wrote this code differently, this might not be a string. So this check happens at runtime. If it was invalid, if this was actually a number 5 or something, if that was the case, then I would get a class cast exception. And so you see that number 5 example right here. If I tried to do this, when I ran the code, it would not work properly. So for objects, you have this exact same idea as you have with numbers. General to more specific must have a cast. Specific to more general, so specific here being the string to more general being the object, does not require a cast. All right, let's update that main function. With these things in mind, I'm going to comment out what I have here. And we're going to write a new array. What I'm about to do is polymorphism. The code I'm about to write, it will be polymorphic code. It'll actually look relatively simple. It will hopefully make sense. We're using inheritance to achieve polymorphism here. That's something that I want to stress. Inheritance is allowing us to do what I'm about to do. There are other mechanisms that we will talk about later in the semester that can get us polymorphism as well. But the main one that you're going to see, at least for now, is inheritance. So I'm going to create an array of pets. Remember our error from earlier. Pet on the left-hand side of the equals didn't cause the error. It was the new pet on the right-hand side that was giving us an error. So I'm going to create a new array called pets. And I'm going to do the same sort of thing that you've seen before with this. Let's throw in, I'm going to copy the spot thing here. Let's do this. So I'm going to create an array of type pet called pets. And I'm going to put a dog in here. And let's put another dog. So I'll have a couple dogs. Maybe let's throw in a cat as well. Why not? So I throw in Mittens, throw in Garfield. And then I'm going to put a semicolon. Notice that this works. So before I had to have separate dogs and cats. Separate dogs and cats, separate array for dogs, separate array for cats. And we've sort of always done this. We sort of said, all right, you say what the type is, and then you put the brackets, and then you can only put that in. But in here, we don't have any pets. There's never a new pet because we can't do that. We made pet abstract. But I want you to think deeper about it. Think about this subtype and supertype thing. Dog is a subtype of pet. Cat is a subtype of pet. What does that mean? Dogs and cats, both of those classes are pets. They're both pets. So if I make an array of pets, then it should make sense that I can put dogs and cats in that array because they are both pets. Dog and cat have what's known as an is-a relationship. So in case you didn't quite get that, a dog and cat is a pet. They have an is-a relationship. And because dog and cat is a pet, we can do something like this. This is polymorphic. We are treating, and this was that definition that I had earlier. The definition was a variable of a supertype can refer to a subtype object. That's exactly what we're doing here. It's exactly what we're doing here. A variable of a supertype, so a pet array, can refer to a subtype object, dogs and cats. So this is polymorphism. Polymorphism in a nutshell here. This one line sort of, as long as you sort of know the background behind dogs and cats and the pet class, this one line is polymorphism. All right. So look back at our slides. Here's that initial code here. I threw this loop in here. This style of loop, this looks different than the style that we've been using. We will talk more about this in the future. If some of you have already used this style before, that's perfectly fine. I typically talk about it a little bit later because it has some important implications with specific, so some other specific types of code that we're going to write in the future. So this is what's known as a for each loop. So it's just saying for every single pet in this array. So you can loop through all the pets in here just by writing a little bit less code. It's not too important for the moment. We're not going to worry about it. The big thing is this pet, this pets array that contains both dogs and cats. All right. So to go a little bit deeper here, and sort of eventually fill out some of the code that we just started writing or that we just changed in our main, we have to talk about a concept called dynamic binding. So when an object's method is invoked, when you call a method from an object, the implementation that's used, so the particular one that actually runs, is determined by the JVM at runtime. So that's dynamic binding. Overloading is achieved at, or at least determining which method runs from an overload, as actually achieved at compile time. Overriding happens at runtime. So Java can tell, the sort of consequence of this is that Java can tell if you've overridden something correctly, and Eclipse will let you know if you have. For overriding, that's not necessarily the case. You may have to run the code just to see that there's an error. What the JVM does when you call an overridden method is that it searches for that method from the most specific to the most general. So it starts further down the inheritance tree and works its way up. Once it finds an implementation, so once it finds the method, it stops and it runs that first found implementation. So we're going to do a few examples of this because it is going to be important for us. So we have two classes here. We've got Poly, and we just have some main class. The main class here calls this method P, and in that method, it creates a new Poly. So this creates a new object. In here, there's no constructor, there's no nothing, so it's just an empty constructor. We just create a new Poly here. Notice what P takes. P takes an object. Well, what is Poly? Poly is an object. Poly is a relationship with an object. Everything is a subtype of object. So this will work fine. Poly goes up here. And then we print out object, this object, dot toString. So we print out the toString from the object that we just created. There is no toString here in Poly. So we just get the standard object toString print, which is the name of the class, at, and then this hash code that represents the memory. So if we drew a little diagram, I would have object up here, and I would have an arrow, and I'd have Poly right here. There's a toString in object. That's the one that prints out this stuff. Poly doesn't have a toString. So as soon as we want to use o.toString, first we look here, the most specific. We don't find it. So then we go up and we look here. There is one. That's the one we use. But if I change Poly slightly and I give her a toString, now when we run, draw some of that diagram again. We've got object that has a toString. And we've got Poly, which also has a toString. So we have two versions of toString. Which one do we use? Well, we always go from, we know that this is a Poly. This is a Poly object that comes in. We're going to print the toString. So we look at Poly first and we say, is there a toString? Yes. And so what would we do? We'd run Poly's toString. So if we ran this, we would see wants a cracker. It would print this out. So that's your basic idea of dynamic binding. You look at the most specific version first of what you are, and then you work your way up until you find the implementation. If you don't find the implementation, the program crashes. If the method doesn't exist, you can't use it. But if the method does exist, it will find it somewhere along that chain. So this is a very easy chain to look at because it's just one class and then object. But we will do some more complex examples coming up. All right. So let's say we have three classes. We've got this class C1 that is empty, just like in Poly initially. We have class C2, which extends C1. And we have C3, which extends C2. It's just empty here. this toString is part of C2. And it just prints out this C2.toString to show you that it's calling it. Main over here creates 3 objects. The first one is a C1. The second one's a C2. The third one is a C3. And then we print out stuff related to all those. Print out object 1, new line, object 2, new line, object 3. So we're going to print out essentially the toString from all 3 of these. Now, I want you to think about the picture. And during our sort of upcoming examples, there are upcoming like a quiz or test stuff, or some of the examples that we might do for some of the review, is to draw out the hierarchy. So we have this first class. This is class C1. There is object above here, and that actually does play a role. We'll talk about it in just a second. We then have C2. And we also have C3. So drawing out this inheritance chain can be important. Let's think about the methods associated with them. C2 has a toString. So I'm going to put toString here. And object also has a toString. And it's useful to put this in here because that's what we're going to be using. If we had some other method that we were using, we could always throw something else in. But this is what our inheritance tree looks like. And we have a couple of places where there's a toString. Now, let's think about C1, because that's the first one we print. We print O1 first. So that's this first string that prints. So we're going to do a toString on O1. Well, O1 is C1. It is a C1 object. So what's the most specific? C1. Does it have a toString? No. We can come over to our inheritance hierarchy here, our inheritance picture, and say there's no toString here. So what do? We go up our chain to the next one, and we see object. This does have a toString. So the output here would be something like C1 at and then a number, because it's going to use the object version of toString. Okay, so now let's look at C2. C2, we're printing, and we see it's an object, but we try to find the toString. So we're printing as a string. We try to find the toString from the most specific, which in our case, we are a C2. So that's our most specific. And we find that there is a toString here. It's right here. So then this will print out C2.toString. Okay. Then we go to C3. C3 is the last one that prints. It's also going to use a toString. So we go down here to C3. We say, is there a toString here? No. Let's go up one to C2. Is there a toString? Yes. So this will print C2.toString. So hopefully you can see the idea here. This is dynamic binding. You go to where you are and you check, does that method exist? If it doesn't, then you work your way up the chain and try and find it. You keep going until you find the implementation. So we had 2 versions of toString, one for object, one for C2, and we ended up printing out the C2 one twice and the object one once in this example. So that's what you would see here. And here, this is just probably one of the runs I did a while back when I made the slide. All right, so visually, and this is basically what I just wrote, at least what I just sort of drew on the previous slide, and I think it is very, very useful. It's very useful to know how to do this yourself. So the instance of C1. So if I create a C1 object, which is what that code was doing, an instance of C1 is an instance of C1 and object. It's both. It is a C1, of course, and it is a object. C1 is the most specific. Object is the most general. Specific to general. So drawing these out can help you determine that as well. It can help you determine, what does it mean to be specific? What does it mean to be general? The more specific we go, the further down this chain we're looking. An instance of C2 is an instance of C2, C1, and object. C2 is a C1, and C2 is a object. C2 is the most specific because that's what we are, and object is the most general. Same thing for C3. C3 is a C2, it is a C1, and it is a object. Object is the most general, C3 is the most specific. So you could use this type of diagram to figure out which toString is going to be called and where you're at in the hierarchy as far as general and specific goes. Okay, so I'm going to go back to the to our pet code, and I'm going to update it so that we actually use the loop. And rather than use this for each loop, especially if you're not as familiar with it, let's just use a regular loop. So I'm going to say for int I equals 0, I less than pets.length, I plus plus. And we're going to print out in here, we're going to do a system out printf. We're going to print out a string and a new line. And so we might do, let's do two strings. So let's say the string and then says and then string like this. So let's do that. And I'm going to say pets I, that's one of my pets. And I'm going to do pets I dot says. So because we're using an array here, this is just one of the pets. This is pet 0, which is Spot in this case, or pet 1, which is Rover, or so on, depending on what I is. Now, if I run this, we get exactly the same style you saw before. Spot says woof, Rover says woof, Kitten says meow, Garfield says meow. Way less code than the stuff that's commented out down here to get basically the same thing. We haven't done this clears throat thing yet. That's something we have to talk about a little bit more. Because if I try to print that, let's say I want to print out another string here. And I want that to be pets I dot has, I start typing has, there is no, this says has or hash code. If I start typing has hairballs, notice there is no autocomplete for me. And if I do that, it says it's undefined for the type pet. So we need to talk a little bit more about how these hairballs for this cat would work. So we're going to leave that off for now and just leave it at this. So a lot less code because I have all of my pets here because of that polymorphism relationship, because of that inheritance relationship. A cat and a dog is a pet. So I can store them into an array of pets. Never in here am I creating a new pet. I'm just creating new dogs and cats, but they are pets. So that's our sort of polymorphism sort of look here. And so it's nice. It's a lot less code to do almost the same thing. All right. So yeah. So this is the sort of output you can expect. All right. Let's do another example of dynamic binding. And we're going to go through and do a trace along with this as well. So the answer to this is this. We're going to go through exactly why the answer to this, where I'm creating a new A and a new B. I'm creating just two objects here. We have A and we have B extends A. So I want to look at A first because that's the easy one here. So let's do the trace. So we start with main. We're starting by creating a new A object. So we come over here to the constructor. A little spotlight on here. So we come over here to the constructor. And technically we call super. Super goes up to object. Object super doesn't do anything, so it comes back down. And we say set I 20. Okay, so we're calling that method. That comes over to here. This prints A set I 20. So it's just showing you what function it was calling. And then it takes this dot I and multiplies it basically by 2I. Whatever I came in as, I'm multiplying that by 2 and setting this dot I. What is this dot I? This dot I is this one. It's this class's I. So it was 7. We didn't use it. we're just saying, all right, we send in 20 here. And so we're going to get 2 times 20. So we're going to set this I to 40. So this dot I is going to be 40 after we run this line here. So we run that line, and then we come back here. We finished with the set I, and we print out I equals 40. That's exactly what we should expect. And then we're done. So we just did the A stuff here. So these first two lines came from creating A. We had 2 prints, we ran the functions, everything here happened. That's with that particular object. Now we're creating a second object. We're creating a B. So here is a call to B. Now remember what happens here. The first line in any constructor is either a call to another constructor in the same class or super. So this is calling super. That's automatic. That's an easy thing to forget. Remember, we talked about the constructor chaining last time. So that's an easy thing to forget. So where does that mean we go? We go up here. We call set I 20. Now, here is the potentially confusing part. What set I do we go to? Well, when we created a new A, we went to this one. But notice that B has one as well. B has a set I. Same thing. It's the same. This is just an override. B's version is an override of A's. So which one do we go to? When you're doing this with methods, it's just like the toString that we talked about. We go to the most specific. We are a B. So when we call a method, no matter where it is, we look to the most specific first, and then we look to the more general. What's the most specific one? The one that's down here. So that's the one that we go to. So we come down here and we print out B.set I 20. We multiply that I that came in, the 20, by 3. So we get 60. And now our I for this object is 60. We finish the set I. That means we just finished the one that was up here. And so we print I equals 60. Now we're done with the constructor on A. So that means we've just finished the super call here. So we just finished that call because we just printed this line out. So we come back here and we print out B, I equals 60, and then we're done. Okay, this was the most complicated one so far. Make sure that you know how this works, why you get these prints, because it has both of the things that we've talked about so far related to this chaining idea. It has dynamic binding and it has constructor chaining, both of which play an important role. And I guarantee you 100% on one of the upcoming tests/quizzes, you will be doing a trace, potentially more than one, where you have to figure out what's the output of this going to be and sort of show what the trace actually is. So make sure you understand this concept, why you get this type of result. All right, there's another operator that plays a role in this as well. It's called instance of, and it tests whether an object is an instance of a particular class. So if I created an object called howdy, or an object called O1 with a string howdy, if I used O1, that's the name of the object, what I've named it here, and I say, is it an instance of a string? This is a question. Is O1 an instance of a string? And this gives me back true or false. Well, in this case, by inspection, just by looking at it, we'd say, yeah, yes. And Java would say yes here as well. If I say, is O1 an instance of a double? Or, if I put this in my other code or something, the code, the dog and cat code, and I said, is O1 an instance of a dog? It would say false. No, it's not. This is how we can do the cat-specific calls. Remember I mentioned the sort of has hairballs thing? I couldn't really do anything with that. This is how we can. So I'm going to show you how that works. So we're going to go back over here. And within this loop, I'm going to ask, is pet I, so is that pet, is it an instance of cat? Cat. Pets I. Is pets I an instance of cat? That's going to give me a true or false. If I get a true, so in other words, if my pet, the pet that I'm the current index of the pets array that I'm looking at, if it's a cat, then I can do some specific things with it. So what I'm going to do is this. I'm going to show you. This is a very common line that you're going to see. I'm going to create a cat called C. And I'm going to do a cast to cat of pets I. This brings us back to something we talked about at the beginning of the lecture. If we want to go from specific to more general, then we need to do, if we want to go from general to more specific, we need to do a cast. General to more specific, right here. General to more specific, we need to do an explicit cast. Specific to more general, we don't have to. But general to more specific, we do a cast. Now I've taken my pet that I know is a cat, because this came back as true. I know this is a cat, so let's turn it into a cat. And so that's exactly what I did. Now we can say if C dot has hairballs, and notice it's now in my autocomplete. So if that particular cat has hairballs, then let's print out the clears throat. And we'll throw a new line in here. Sure. The formatting here will be a little bit different than what's in the than what's in the slides. So if we run this, oops, my where are we at here? I had the extra %s from when I showed the thing earlier. Do that, and there we go. So now you see that Mitten clears throat because Mitten has hairballs. This right here is how you determine what to do if something is specific that you need to do with a method or something that only exists in that specific class. Hairballs does not exist within pet, so I cannot call it from pet. Says does. Says exists within pet, but hairballs does not. So if I want to deal with hairballs, I have to make sure, is that pet a cat? If it is, change it from a pet to a cat, and then I can call all the methods on it. That's the idea. And we're going to do this one more time with another special method similar to toString. All right, so that's the change we made right here. If P instance of cat, turn it into a cat, and then do all the hairball stuff. And so we get something that looks like this. Of course, the formatting is a little bit different because I have new lines in different places, but that's the idea. Now, compare that to what we had written before, to that commented code that I have in the Eclipse file. It gets the same result, but way less code that we had to write. A little bit more understanding was necessary. It took us a little bit to understand why this works, how this works, some new syntax. But in the end, it helps us write a bit less code, which is always welcome when we're programming. All right, so the last thing we're going to do is deal with the equals method. It compares the contents of two objects. You've used it before with strings. So to compare two strings, the contents of two strings, use the .equals method. There is a default implementation. Object has an equals method, and it looks exactly like this. It's just return this equals object. That's all it does. So I'm going to show you how to sort of write an equals method, and we'll sort of mess around with this sort of later on. So let's say we have main. Now let's say we have our pet.java file where there's no equals method defined. So we have all that other stuff in there, but there's no equals method. If I wrote this particular code, here we basically have a lost dog. And so in our database, we have two dogs, D1 and D2, and we have their ID. And then we find a lost dog. And maybe we scan its little infrared chip and we see that it has ID of 1. So in our code, we'd want to look through all the dogs and compare them. So is D1 equal to D2? Well, their name doesn't really matter. It's the ID that matters. So clearly, just by looking at it, we say that no, these two dogs are definitely different. They have different IDs. Is D1 equal to lost? Well, a lost dog has an ID of 1. D1 has an ID of 1. Yes, this should be correct. But there is no equals method defined in dog or in pet, which means we only have the object version of equals, and that would give us false in this case. D2, does that equal lost? This is also going to give us false. We know it's not because we should be comparing the IDs. Because again, we don't know the name of the lost dog. We just know the ID. So we should be comparing IDs, but that's not what object does. Object compares the memory location between the two objects, which doesn't have anything to do with the IDs of the dogs. So we would just get all false for this. That's not what we want. That's not going to work for us. So we would need to write an equals method. This is exactly the same as writing toString. So let's go do that in the code right now. Then I'll show you what the usage looks like on that slide. So I'm just going to put it underneath toString here. And this is going to be at override. We're going to put that annotation in. And then I'm going to put in public Boolean equals. And this takes an object O. So we can take any kind of object that we have. Remember, everything is an instance of an object. So we can take anything in. But we need to check. Is O an instance of a pet? Because if it's not a pet, then it doesn't make any sense to compare it. So if it's not a pet, if O coming in is not a pet, then my else here is going to be return false. If I send in a number and try to compare it to a pet, then they're obviously not equal. And so we can just give back false right away. But if O is a pet, then we need to convert O to a pet, just like you saw in the code with dealing with the cat and the hairballs. So you would say pet P equals a cast to pet of O. If O is a pet, then let's turn it into a pet. And then we can return, and this is if you look in the code on the slide, it actually uses the dot equals for a number. So there's multiple ways to do this one. We can do something like this. We can say if the p dot, actually we don't have, the p dot id equals this dot id, then we can return true. So if the IDs are the same, we return true. Otherwise, we return false. The code in the slides is a little bit more compact, but this is the idea. If the object is a pet, turn it into a pet, and then do whatever we want to do for the comparison. So we're just going to compare the ID. We're not going to worry about the name. We're just going to compare the ID. If the IDs are the same, then we know the pets are the same, and the equals should be true. If they're not, then we'll say false. And if O isn't even a pet, then we say false. So with this style of dot equals, or the equals method, with that style in there, we would get the correct value. We get true for that second D1 dot equals lost. We would get true because their IDs are the same. That's the idea of equals, and we will work with equals a bit more in the future. But what I want you to pay attention to most right now is this idea of using instance of. Checking if one object is an instance of another. And if it is, then do the conversion. That should be sort of a default thing when you're thinking about using instance of. If something is an instance of something else, convert it and then do whatever it is that you need to do. So this will be important in the future. All right, so the take home from this week is that inheritance lets us create a general class like pet, and then share that code that you wrote in the general class among other classes, the subclasses. And those subclasses can be specialized as needed. A cat is different than a dog. There was the sort of hairball stuff that we put in. The idea of constructor chaining, method overriding, especially overriding versus overloading. Make sure that you can tell the difference between what they are. Final methods can't be overridden. Final classes can't be subclasses. And classes that are abstract cannot be instantiated. Polymorphism lets us write code that works with different subclasses that share some common superclass. And you need explicit casts when going from super classes to subclasses. Dynamic binding means that you're going to call the most specific version of a method first before moving up the inheritance chain to find a different version. The instance of operator allows you to determine at runtime if an object is of a particular class. And then the equals and the toString methods have default implementations in object, but we can override them in our own classes to do specific things, to allow specific types of comparisons between objects and to print the object in a way that we like. So that's some of the take-home stuff for these two lectures. This is a complex topic. And the examples here, even if you followed along with pet and dog and cat, they're not good enough to know how and when to use them. So this is what some of our sort of project stuff is going to be based on. Blackjack will have inheritance. It will have polymorphism in a similar way that we did polymorphism today. So in class, in the in-person class, we will start Blackjack. So I'm going to give you sort of an overview, and then we'll start writing at least one of the classes. In lab, this week, this sort of coming week on Friday, we will be doing Lab 2. We'll be doing LA2 graded, and PA3 will not be assigned this week. It will be assigned next week. So you'll have sort of a week off from homework, but we will have a lab on Friday that you will need to do. So that is it. So next time we'll come back with a bit more OOP stuff.